In this video, we're going to continue our discussion of curve fitting. And in particular, we're going to talk about linearization of nonlinear relationships. So in the previous two sections, the model function y was formed as a linear combination of functions f1, f2, up to fm. The minimization of the sum of the squares of the differences between the model prediction and the data produced a linear system of equations to solve for the coefficients in the model. In that case, y was linear in the coefficients. In certain situations, however, it is possible to convert nonlinear relationships to a linear form. So for example, consider the model shown here, where y is an exponential function in x. So y is equal to b1 times e to the power of a1x. So this model is nonlinear in x, and it is nonlinear in the unknown coefficients, which are b1 and a1. However, it can be transformed into a linear model. So we can take our function y is equal to b1 e to the power a1x, take the natural logarithm of both sides, gives us the natural log of y is equal to a1x plus natural log of b. We can call this ln y as v, a1x we can call c1u, and ln b we can call c2. So this equation is linear in the coefficients c1 and c2. So we can use our techniques to solve for these coefficients, c1 and c2, and then we can transform back to the original coefficients using the relationships shown here, where b1 is equal to e to the power of c2 and a1 is equal to c1. So here are some examples of other nonlinear functions that can be transformed into the linear function v is equal to a0 plus a1u, or something of that similar form. So the one we just talked about is the exponential function as shown here. So what this table shows is for the function, what we would want to define as our v, what we would want to define as our u, and then the relationship between the coefficients. So what is a0 and what is a1. And then this, putting these into this form, v is equal to a0 plus a1u. So another example is a power function, so where y is equal to c0 times x to the power of c1, and these other functions as shown here. So all of these we can linearize into this form, v is equal to a0 plus a1u, and then we can use our techniques for linear regression to find our coefficients a0 and a1, and then we can use these relationships to transform back to the original coefficients in the original equation, which in this case are labeled c0 and c1. For nonlinear relationships, the coefficient of determination is not a very good measure of how well the data fits the model. In fact, different software will give different values for r squared. In contrast, in linear regression, the coefficient of determination has a very well-defined definition and is a good representation of how well the data fits the model. So in this nonlinear relationships, we will cautiously use the coefficient of determination for nonlinear relationships as defined as shown here. So it's a similar definition as it was for linear relationships, where we have r squared is equal to 1 minus the sum of the squares of the residuals divided by another sum of squares, and in this case it's just the sum of the squares of the original data points. So again, it still kind of has the same definition. R squared is equal to 1 minus the residual sum of squares divided by the total sum of squares. So let's look at an example. We have some data given here, and we want to use an exponential model to fit this, which has the form y is equal to b1 e to the power a1x. So the exponential model can be linearized as follows. So this is our model, y equals b1 e to the power a1x. And we can take the natural log of both sides and write it in its linear form as shown here. So the data needs to be converted to x ln y. So x stayed the same. You can see our u was equal to, our u is just equal to x, and v is equal to the natural log of y. So basically we're going to use vi and ui to represent the converted data, with vi is equal to the natural log of y, and ui is equal to xi. So this was our original data, and this is its converted form. Now we can use the linear regression procedure from section 9.2 to find the best fit for the model. So we have our model as shown here. So we're looking for C1 and C2 in the expression here. So we know the how to define, or how to write C1 and C2 directly using the linear model regression. So C1 is given by this sum, or collection of sums here, and we can plug in all our values and get the equation here, and we see that C1 is equal to 1.5976. And then C2 is given by this expression here, where we plug in our value for C1, and we plug in the rest of our numbers, and we get that C2 is equal to negative 1.0709. And this is just putting, setting it up in Excel so you can see where all the numbers come from, and how these sums come out, so you can go back and see kind of where those end up in the expressions. So here I've got my original data, x and y, and then my transform data, u and v. And now we can calculate the coefficients of the original model. So A1 is just equal to C1, which was 1.5976, and B1 is equal to e to the power of C2, which is e to the power negative 1.0709, which is 0.3427. Therefore, the best exponential model based on the least squares of the linearized version has the form shown here, where this was my B1 and this is my A1. And we can also do this in Excel. So just plotting a scatter plot of the data as the black dots, and then adding an exponential trend line and showing the equation on the chart, we get the same equation as shown here. Now we could calculate the coefficient of determination for the linearized version of this model. However, it would only describe how good the linearized model is. So instead we will use our expression for the nonlinear model for the coefficient of determination as shown here. Again, we can set this up in Excel to calculate the various sums and various quantities. And in particular, this sum here is given by this column, and this sum here is given by this last column. So we can plug in our numbers and see that r squared is equal to 0.998. And we can also do this in Matlab, where this Matlab output shows some of the intermediate values and ultimately shows the parameters a and b along with the coefficient of determination. And here's a plot of the model fit with the original data. Okay, let's look at another example. We want to use a power model to fit this data of the form y is equal to b2x to the power of a2. And this is the same data that we had in the previous question. So the power model can be linearized as shown here. So y is equal to b2x to the power a2. We can take the natural log of both sides, and we see that we've got natural log of y is equal to a2 ln x plus ln b. So the data needs to be converted to ln x ln y, and we'll use vi and ui to represent the converted data, where vi is equal to ln yi and ui is equal to ln xi. So this is our original data and our converted data. So just taking the natural log of all of the elements. Again, the linear regression procedure can be used to find the best fit for the linearized model. So the linearized model we can write in terms of v and u, and we're looking for these coefficients c1 and c2. So we can plug in our values to calculate our c1 and our c2. So c1 is equal to the values shown here. So we find that it's 2.4387. And c2 is equal to the expression shown here, and we plug in our value for c1 along with the rest of our values, and we get that c2 is equal to 0.4093. Again, we can set this up using Excel. So this is the original x and y, and the converted u and v, and then our ui, vi, and ui squared. So the sums that we're interested in are at the bottom row here, and those were all plugged into our previous, the quantities on the previous slide. So now that we know the coefficients of our linearized model, we can calculate the coefficients of the original model. So A2 is just equal to C1, which is 2.4387, and B2 is equal to e to the power of C2, which is 1.5058. So the best power model based on the least squares of the linearized version of the data has the form shown here. Y is equal to 1.5058 times x to the power 2.4387. Again, we can do this using Excel, so just plotting a scatter plot and fitting a power trend line, we can show the equation on the chart and we get exactly the same expression. So for the nonlinear model, again, we're using the coefficient of determination as shown here. We can set up our table in Excel and calculate the relevant sums and quantities, and in particular the sum of the squared, or residual sum of squares is 3.25, and the total sum of squares is 479. So we can plug those in and we see that r squared is equal to 0.9932. And again, we can do this using Matlab, and the output is shown here with, again, the same model parameters and r squared as well, and the plotted fit along with the data.